as promised, another reaction of 1,3-dicarbonyl compounds. And this reaction is called a decarboxylation reaction. So upon heating, carboxylic acids with a carbonyl group at the beta position, in other words, a 1,3-dicarbonyl, undergo a reaction in which they lose a molecule of carbon dioxide. Okay, so a couple of examples. So first, if we start with a beta keto acid and heat it, you end up with a ketone plus carbon dioxide. In other words, we have broken a carbon-carbon bond. A second example, instead of a beta keto acid, you can also use a beta diacid, so a dicarboxylic acid. Heat that up, and now we have a 2-carbon, in this case, plus the R group, carboxylic acid plus CO2. Okay, so recall that a beta keto acid can be prepared through hydrolysis of a beta keto ester. And a beta keto ester, of course, is the product of a Claisen condensation. So that's why we're talking about this reaction in this context. Okay, so the mechanism of this process is somewhat unusual, at least in the laboratory. Well, it's not that unusual. There's actually a lot of reactions that go through this mechanism. We just haven't met any yet in this course. And it is what is called a pericyclic mechanism. And what pericyclic means is that you have 3 arrows, if you look at this mechanism, that follow each other around in a circle. This is a one-step mechanism with no intermediates. Okay, so in one of those arrows, the ketone, or in this case, it's actually the other carboxylic acid, we're using the example with the diacid, goes and picks up the hydrogen from the carboxylic acid. It's using the electrons in the CO pi bond to form a new OH bond. That involves breaking a bond from the carbonyl carbon. So that means we have to add another bond to the carbonyl carbon, and we use the electrons in the carbon-carbon sigma bond in order to break the carbon-carbon bond and form the new carbon-carbon bond so that the carboxylic acid carbon has 4 bonds. And then finally, the electrons that are left behind on what was the carboxylic acid form the second CO pi bond to kick off carbon dioxide. Okay, the driving force of this reaction is that carbon dioxide is a very stable molecule, and it is a good thing to kick off as what is essentially a leaving group, although this is not a substitution reaction. So after going through the process that I have described, you end up with an enol. Okay, so a carbon-carbon double bond and an OH. And then the enol, of course, is going to undergo tautomerization, in this case, back to the carbonyl group, and that will give you the carboxylic acid product that you expect out of this reaction. So this tautomerization, of course, is going to be very favorable in the direction shown because you would rather have a CO pi bond than a CC pi bond. All right, so why do we care? I mean, in general, we have started this unit by talking about reactions that form carbon-carbon bonds that bring smaller molecules together to make bigger molecules and increase molecular complexity. Well, here's a reaction that breaks a carbon-carbon bond and decreases molecular complexity. Well, the reason we care is because decarboxylation reactions are actually very important in biochemistry. It's an important reaction because all of the carbon dioxide that you breathe out is generated through a decarboxylation reaction somewhere in metabolism. Okay, so each turn of the Krebs cycle generates 2 molecules of carbon dioxide. So the net reaction of the Krebs cycle is that you take a molecule of acetyl-CoA and you generate 2 molecules of carbon dioxide plus a molecule of CoA. So those 2 molecules of carbon dioxide are generated in 2 different steps of the Krebs cycle, but they still eventually end up getting expelled through respiration. So we're going to look in detail at one of these carbon dioxide decarboxylations because mechanistically it resembles what I showed you on the last slide of decarboxylations that take place in the laboratory. And that is the step of the Krebs cycle in which isocitrate is converted to alpha-ketoglutarate. So the reaction is drawn below. Now, you may be looking at this mechanism and not seeing 3 arrows following each other strictly in a circle. You may not, at least in the starting material, be seeing a beta-keto acid, and you may not be seeing any carboxylic acids, period. And if you have observed all those things, you are absolutely correct and quite observant. So the disclaimer that I have to interject at this point is that mechanisms are a little different in the body than they are in the laboratory because, first of all, we cannot heat things up in the body. We have to be working at 37 degrees. We have to be working at physiological pH. And that becomes important because at physiological pH, carboxylic acids are deprotonated. Okay, so carboxylic acids have a pKa between 4 and 5. At pH 7.4, the pH is above the pKa. So based on the Henderson-Hasselbalch equation, they will exist primarily in the anionic state. And as is drawn here is all of the carboxylic acid groups in isocitrate are actually deprotonated, to make the 3 carboxylate anions. Okay, so since you don't have a carboxylic acid, you can't remove the carboxylic acid hydrogen as a step in the mechanism and transfer it over to the beta carbonyl group. But if you look carefully at what's happening in this step that has the 3 arrows, magnesium 2+ is taking the place of a proton. Okay, so when you're adding extra electrons to the carbonyl oxygen, that extra electron density is dealt with by coordination to magnesium 2+, just like we saw magnesium 2+ interacting with carbonyl oxygens in the course of ATP hydrolysis. Okay, so mechanistically, what's happening in the course of the transformation of this thing labeled unintermediate in the reaction is that you form carbon dioxide by taking the electrons on the negatively charged oxygen of the carboxylate and using them to form a CO pi bond. You break the carbon-carbon bond to expel the CO2. Those electrons go to form a CC pi bond, just like we saw before. And then the electrons from the ketone CO bond go onto the oxygen, and in this case, they are coordinating magnesium 2+. So once again, we have an enol that is formed initially, which undergoes the favorable tautomerization to give the ketone, and that ketone, of course, is the keto of alpha-ketoglutarate. Okay, so there's one more piece of this that I haven't dealt with. And that's, I showed you how to get from this thing labeled unintermediate to alpha-ketoglutarate, but this intermediate, which is a beta-keto carboxylate, is not isocitrate. So the first step in this whole reaction is that isocitrate, which has a secondary alcohol, is the secondary alcohol of isocitrate is oxidized to a ketone. And NAD+ is nature's oxidizing agent. So NAD+ does the oxidation, generates NADH and H+. The secondary alcohol is oxidized to the ketone. And now, once we carry out this oxidation reaction, we now have something that is set up for decarboxylation. And it's actually good that that happens, because if isocitrate, if the actual isoluble intermediate from the Krebs cycle were capable of undergoing spontaneous decarboxylation, it would happen too rapidly. The oxidation state sort of acts as a gatekeeper on this reaction. Okay, so this is the formation of one molecule of carbon dioxide. I want to just briefly mention to you the other important decarboxylation reactions in metabolism. And the first one is the conversion of pyruvate to acetyl-CoA. So you might remember that in glycolysis, a molecule of glucose is broken down into 2 molecules of pyruvate. So that's the end product of glycolysis. But as I have just said on the last slide, the input into the Krebs cycle is a molecule of acetyl-CoA, which has only 2 carbons, whereas pyruvate has 3 carbons. So in order to convert pyruvate into acetyl-CoA, we have another decarboxylation reaction that happens. And this reaction is catalyzed by a series of enzymes and coenzymes called the pyruvate dehydrogenase complex. Then the second example of loss of CO2 through decarboxylation is actually the very next step in the Krebs cycle after the one we looked at in detail on the last slide, and that is the conversion of alpha-ketoglutarate to succinyl-CoA. Okay, so in this case, you can see that the terminal carboxylate at the end of alpha-ketoglutarate that has the ketone on it gets lost. It gets converted into CO2, and then that group is replaced by an S coenzyme A to give you succinyl-CoA. So in both of these reactions, the compound that is decarboxylated, if you look at it carefully, is an alpha keto acid rather than a beta keto acid. Okay, furthermore, both of these reactions involve coenzyme A and also other coenzymes that I'm not even listing on this slide. The mechanism of these reactions is different from the mechanism we looked at on the last slide and the one before it of fundamentally the beta keto acids undergoing decarboxylation. So within this lesson, we are not going to cover these particular reactions in detail, but you just need to know that under biological conditions with the proper set of enzymes and cofactors, you can decarboxylate alpha keto acids as well as beta keto acids, even if you can't do that in the laboratory. Putting all of these reactions together, that's how our molecules, the carbon atoms of a glucose molecule and other sorts of food that you eat, because everything ends up eventually going through acetyl-CoA, gets converted into carbon dioxide to be breathed out during respiration.